All right, welcome back everybody. I'm Richard. This is still Very Little Evolutionary Game Theory. In the second lecture today, I want to transition from the models we built in the first lecture to a new topic. It will feel like a new topic, but as I want to show you, it's really the same topic. So it'll be exciting and then boring. No. So we will continue analyzing simple game theoretic models of social behavior. And last time it was about conflict, framed as a story about conflict over a finite resource. Today I want to talk about cooperation. It's in some sense the complement or antagonist of conflict. And I want to show you a few things about these models. Their basic structure, their relationship to the conflict models from last time, and some additional evolutionary dynamics and how to solve for them in these models. So the idea for studying cooperation is first you've got to figure out what you mean. So a huge amount of the evolutionary game theory literature, probably most of it, is about cooperation, defined somehow. It's really the obsession of the field. And it's an obsession because we think of cooperation as behaviors that generate common benefits. So human societies are full of things like this, and humans are obsessed with cooperation. Right? There's lots of activities you do either willingly or under coercion from others that will generate, at least you believe, common benefits for a larger group to share. But the costs are at least partly private. Meaning they're yours alone. Yeah, you take an action, you expend some of your time and energy or money. You may benefit directly from your action, but others do as well. That's the common benefit. And these sorts of scenarios are often called, in English, cooperation scenarios. And we see the potential for this, and sometimes its realization, in many animal societies. I should also include plants. Also in plant societies, plants are people too. They also have social behavior, right? They're just slow. Yeah, but plants as well have social lives and engage in cooperative acts or not. In animal societies, you could list tons of things. I mean, human societies, we have taxation and lots of hierarchical stuff that even takes the control of the cooperation away from you, right? But simpler animal societies, you have lots of things like territory defense would be a common one, where there's some common territory, individuals live in it, everybody benefits from some patrol of the territory to keep the other groups out from stealing your food, something like this. This happens in lots of animal societies. But since the ones doing the patrolling are paying a cost for it, they're doing that instead of feeding or whatever it is that they want to do with their free time. There's private costs. So there's collective benefits, common benefits, and private costs. And I will leave it to your fertile imaginations to think of many, many others. But I want to work with this territory defense model for a second, and let's make a model of it so we can explore it a little bit. I want you to imagine, as in the previous lecture, we're going to have a very simple game theoretic model with two strategies. Remember, last time I introduced the classic evolutionary game theory model of conflict with hawk and dove. Now we're going to imagine territory defense, so we're not going to have hawks and doves because they're not fighting over the territory. They already both live in it, these individuals we're modeling, but they have different tactics when it comes to territory defense. The first I'm going to call rest. And rest does not do anything for the territory. They rest. So when it's their turn to patrol, they rest. Sounds nice. Yeah? And so that's the first strategy that we put in the payoff matrix that we're drawing. And the second strategy is the one that patrols, and I will creatively call that one patrol. So now, like in all of these simple two-player games, we try to fill in this matrix using our assumptions about the scenario, the behavioral scenario. So when two rest meet, I'm just going to make this the baseline. I'm going to make that a 0. That doesn't mean they die. Remember, the entries in this matrix are changes in fitness. So that means there's no change. So I'm just setting the baseline there with rest. Remember, this is Richard's famous trick for doing effective applied math. Make something 0. Yeah, you want something to be 0. Right, this just sets the scale of measurement. Zeros are real nice. Okay, rest is paired with a patrol in a group. So your lazy rest, take the perspective of row player. Yeah. What payoff are you getting? Well, you get the benefit of somebody having patrolled, but you paid no cost for it. So the benefit, I'm just going to write little b. I can make up a symbol, right? I'm making the model. I'm God, right? I make the benefit little b. So this is a variable. It's adjustable. Whatever the common benefit of somebody patrolling the territory is, it's shared among all individuals, and they get little b. So that's more food in your territory, fewer aggressive invaders, whatever it is that you're defending. Patrol, when you're patrol and you meet arrest, it's the flip side of that. And now what happens is you still get the benefit because it's a common benefit, right? You did the work, the territory is defended, yay. But you paid a cost. So I'm going to invent another symbol here, which is little c for the cost. So now the one who does the patrolling gets a benefit, but their net benefit is smaller because they also paid a cost to do it. You're all feeling this, right? You live with people? Yeah, you have housemates? Mitbewohner? Yeah, this is, so this is where your mind goes, yeah, when you think about this. I have a version of this called the doing the dishes game. Can really make it elaborate as the course goes on too. I could show you, because next week we're going to do reciprocity, where you actually live with the person, and yeah, so this will really, if you've got housemates, this is going to...
Tragedy of the commons.
Yeah, this is the tragedy of the commons is in here. The tragedy of the dishes, as we would say, or the milk, or whatever it is in your particular household that causes problems. One last thing here is patrol and patrol. So what happens when you both patrol? You can assume a lot of different things here, and I'm going to assume one particular thing. But the idea here is we need to figure out how they share the cost. And cost sharing is a mechanistic assumption, and you can choose different things depending upon how it actually works. Ideally, there would be some empirical investigation involved to see how these costs scale. How much time is saved if 2 patrol rather than 1, something like that. You could do something actually interesting and fun that way. I'm not going to do that. I'm going to do the algebraically simple thing, because this is an introductory course, and we'll just assume they split the cost. So if you both patrol, each of you pays half the cost. That may not be true, right? Because the scaling may not work that way. There could be synergies to you both doing the work such that the total cost is smaller. Yeah, or the opposite. Sometimes when all scientists know this very well, you add people to a project, sometimes the costs go up, right? Because there's coordination costs. Yeah, it's not just scientists, but often. Yeah, no. Does this make sense? All right, so this is a little sandbox for us to think through this kind of basic cooperation dilemma. What's the dilemma, you might ask? And that's what we're going to pull out. And we're going to pull that out by analyzing the game using what I taught you last time. We're just going to do it again. And what are the steps? This is also my chance to reveal to you that you learned steps for doing analysis of simple 2-player games. So the first thing we're going to do is we're going to ask, are any strategies ESS, right? Are any of the strategies evolutionarily stable strategies? And remember, the way we're going to ask that, I'm going to do this, but I'm just going through the recipe right now. So the way we're going to do that is we're going to imagine a world in which each of the strategies is common, and there's a rare invader from the other strategies. And we ask if that rare invader can increase. What are the conditions? And so a strategy is an ESS if there are some conditions under which the rare strategies will not increase. It will be stable in the presence of rare strategies. Does this make sense? There's lots of different ways to say this, and this phrase, evolutionarily stable strategies, it doesn't really roll off the tongue, right? So, but it's the idea of when you're common, can you do better than the rare invaders in the population? Once we've done that, we're going to ask, are there any stable mixes of the strategies, which is what we had last time, remember? There was a situation where the strategies, neither strategy is an ESS, but there was a stable mix of them, and we derived that for hawk and dove. Remember, hawk can't live with itself, dove can't avoid getting beaten up, so you get an internal equilibrium in the hawk-dove game. Yeah? So we're going to ask if that happens here. And now we're going to have a third thing to ask. Are there any unstable mixes? Right, which seems like a weird question because of course there are, but this will have a particular answer flavor to it, which is the flip side of number 2. There will be equilibria sometimes in models which are stable because they're equilibria, but if you perturb away from them, the system doesn't go back to them. These are often called unstable equilibria. Yeah, and that's what we're going to find. So I should write that here. Mixes / equilibria. And these happen a lot in cooperation models. So I want to show you an example of one. Okay, good. Are we ready to proceed? So let's do it. Let's take number 1. You're pros now. You've had one class. Yeah. Some of you have even done the homework. Thank you. And are there any of these strategies ESSs? So we'll just take them one at a time. Let's take rest. The condition for rest to be an ESS, you folks can do this, but I'll walk you through it. You can analyze it with your eyes in the matrix. It's simple enough. For any strategy to be an ESS, how it does against itself. Remember, when it's common, it meets itself. That's what has to be beaten by the invader. Rest against itself is 0. And you're thinking, can I do better than 0? Not necessarily, right? Nature is cruel, to say in a Disney movie, right? So, rest to be ESS requires that 0 be greater than whatever the invader gets, right? Because the invader now is going to come in and it won't meet itself, it meets rest. So the invader against rest. So it's rest against itself must be greater than the invader against rest. Right? The common type, everybody faces the common type, even the invader. And that is what? Patrol against rest. Right? So you're now the rare patrol, but you're still going to meet a rest individual, so you get B minus C. Does the logic make sense? So if you can do that, you can analyze every 2-player game. Yeah, but you just got to get that logic. So I ask the students, when is this true?
B is larger than C.
Well, B is less than C. Yeah, the other way around. Right? Got to keep our inequality correct. Most common sources of algebra errors in applied mathematics is inequality going the wrong direction in some factor of 2. Somewhere in that you just lost, right? Happens all the time. Does this make sense? Okay, so what does this mean? Again, we've got the interpretation. So the algebra is correct. What does that mean? If your private share of the benefit from cooperating is less than your private cost, then a rare patrol will not invade. Which in hindsight is sort of obvious, right? We made the assumptions of the model, and what B less than C is saying is that for the first individual who patrols, their private costs exceed the benefit of the patrol. And in that case, natural selection will not favor patrolling. Like, duh, right? But again, with all these, I told you last lecture, game theory is incredibly stupid. Yeah, but we are dumber, and so it actually helps us, right? Of course, this result is a consequence of the assumptions, but it's not transparent when we write the assumptions down what the consequences will be, and that's the benefit of doing this sort of analysis. Yeah. Does this make sense? Okay, so we've got a condition. Rest can be an ESS if that's true, but that's a terrible world, so let's assume that's not true, right? Let there be some benefit to cooperation. That said, or I'm going to loop back to this actually, so I'm getting ahead of myself. This can be true even when this is positive, right? So it could be true that B is greater than half the cost of patrolling. So it might be that it can't invade a population, but, as we're going to pivot to next, if everybody were rest, you'd all be better off. And that's what's going to happen in a lot of these models. Yeah. Okay. Patrol ESS. Patrol to be an ESS, patrol against itself. Gets that? Right? So world, everybody's patrolling. Right? First mutant rest appears, is paired with someone who patrols, and therefore gets B. Yeah? One way you can think about these is, since you're a row player, you just put the common type strategy in the column and you stay in that column. So with rest being common, we just started here, got 0, and then that has to beat that. With patrol being common, we start with patrol, and then it's got to beat that. But you always stay in the same column because everybody faces the common type. Does that make sense? Okay. So this is something you can analyze with your eyeballs. Yeah? Does this look good? No, there's a problem here, right? So, I mean, you could do some algebra and reduce it down to a condition that has to do with C not being a cost, right? This is what this says. It's like, yeah, patrol could be an ESS as long as it doesn't cost anything. That's a basic problem, yeah. So this is a no. This is a big no, yeah. C would have to be negative. That's what would have to be true, which is not what we're analyzing. So this situation that we're looking at here with if B is less than C, so you could think about it, we could draw, sorry, I need my eraser. We could draw out this model like we drew Hawk-Dove before. We've got patrol on one end and rest on the other. Yeah, this is the whole space of the game, right? Remember before we had Dove on the left and Hawk on the right? And now I've got patrol, that's like Dove, right? It's a nice strategy. Yeah. And we've got rest on the right, that's like Hawk. Although Hawk here does nothing, right? Feels different. If B, and I just showed you that patrol is never an ESS, right? So the dynamics take you up from there. Starting to feel like Hawk-Dove now, isn't it? Yeah, okay. And there's a condition for rest to be an ESS, and that is, yeah, B less than C. But if that's violated, then you've also got dynamics to take you in from here, because it could be worth it to patrol on your own. Yeah. In that case, it's Hawk-Dove. There'll be some, it has the same, the exact quantitative dynamics are different where you come to rest, but the total evolution dynamics are the same as Hawk-Dove. There will be some point in the middle where you'll get a mix of the two. Or it's true that B is less than C, in which case you get no patrolling. Yeah. And that situation, which is like in the Hawk-Dove game when V was greater than C, so that cost of injury did not deter Hawks and you got all Hawk world. Okay, that's what we're getting. The same dynamics here. This looked like a cooperation game, but it's actually Hawk-Dove. And Hawk-Dove looked like a conflict game, but it's actually a cooperation model. Yeah, it's just in your mind's eye how you label things and think about the intent of the strategies. Is this disturbing at all? If so, good. That's the point. Yeah. Yeah. The math don't care about your interpretations. And finding these structures across models that feel the same to us is one of the really nice bonus features, I think, of doing applied math. Right? There'll be these mathematical structures that repeat across things that seem really different, and that's really nice. I get tingles every time I find something like that. I want to bring that sensation to you. Okay, it's wonderful intellectual discovery. When B is less than C, and you're in this version of it where everybody ends up rest, this is often called a prisoner's dilemma, which you've heard before, probably. And if you haven't, that's fine. Prisoner's dilemma is a label for a particular kind of cooperation dilemma in which no matter what your opponent does, you are incentivized to do the antisocial or uncooperative act. So think about that in terms of this payoff matrix. We're going to imagine B is less than C, so that if you're the first person to patrol, it doesn't benefit you. Your private share of the benefit is not enough. Then we can just use the game matrix to analyze this by imagining what you are. So whether it would be in your interest to switch. So imagine your opponent plays rest. So you're in this column, and now I want you to pick a row that is to your benefit. Have you picked a row? Which row do you want? Yeah? Yeah, so you would, if we assume B is less than C, then you're going to choose 0, right? So if you knew your opponent was going to rest, you would rest. Okay, and now we move to the other column. If you knew your opponent was going to patrol, which of these columns would you choose? I mean, which of these rows would you choose? You would choose the top one again. You would choose to rest again. That is the prisoner's dilemma dynamic, where no matter what your opponent, even if you were psychic and you could know ahead of time what your opponent would do, you would still always do the antisocial thing. Or evolution would. Yeah, let's not personify it too much. Yeah. And that is my super heuristic, folksy definition of a prisoner's dilemma. There is a more detailed definition in the notes, and it has a particular meaning, but the spirit of it, captured by the folksy definition, is this puzzle that no matter what the other individuals do, you're better off doing the antisocial thing, and yet both of you would be better off if you could just do the social thing. Because when you both rest, you get 0, but if you could both patrol, you would get B minus C over 2, which is greater than 0. We assume, right? That can be true. It can be true that if everybody did the pro-social thing, patrolling, you would be better off individually. Forget the group, you don't have to care about the others, but you individually would be better off if everybody were patrolling, and yet you're all resting, looking around. Why won't anyone here patrol? Yeah, does that make sense? Okay, that's the fundamental issue. And the details of cooperation models vary a lot. And they're not all prisoner's dilemmas. I want to show you some other examples so that you don't leave here thinking that they are. But what they all share in common is this conflict between the individual and the group. And what I mean by conflict between the individual and the group, obviously individuals aren't fighting the group. It's a conflict of interests in a sense. Like if the cooperative strategy is common, what that means when we're talking about cooperation is that on average individuals in the group get better off. So as you add more cooperators to a group, everybody's welfare increases because nice things are happening in the group. There's less noise, there's less pollution, there's more patrolling, stuff like that. Yeah, whatever you define as the cooperative behavior. And yet individuals are better off if they switch. Right? Remember, no matter what the other individuals are doing in a prisoner's dilemma, you're better off if you switch to the antisocial thing. Yeah, even if that produces less of the common good, because your private cost exceeds it. Does that make sense? That's a prisoner's dilemma. Equally important. I would say I think, but I think everybody thinks this now. You never know. I'm strange, so I'm not sure if people agree with me, but I think this opinion is now completely standard. Just as important are things that we would call coordination games. Usually not cooperation, but I think of it as a kind of cooperation. Coordination is another one of those poor, abused English words like cooperation that has been brought into service of some highly technical literature. And if you use it in everyday life, it will mean something different than it does in the technical literature. So probably the best way to define what coordination means in game theory is to show you a payoff matrix. So I apologize for doing it this way, but this is a case where, yeah, years of scholarship have destroyed the core meaning of these things. I think in colloquial English, cooperation, coordination are kind of synonymous in most cases, but they're really technically different in game theory. So now let's think about the classic coordination game that everyone uses, and I'm going to use it too, because it's my job to teach you the classics, comes from moral philosophy, and it's called the stag hunt. So the idea is, in the most primitive sort of human society, this is what philosophers think about. There are two hunters and they have a choice of which prey species to hunt. They can do the social safe hunting strategy, antisocial individual safe hunting strategy, which is to like set snares for hares, is the idea. Yeah. And the safe strategy delivers a small benefit B, like whatever you catch in your traps. But you don't require the cooperation of the other individual in your group for this. The other strategy I'm going to call risky. The risky strategy is to hunt a stag in the classic story. But since it's risky, it benefits from cooperation. And you really need the cooperation to pull it off. So the idea is in the story that if both individuals decide to go for the risky thing, hunt the stag, they can get a very large benefit, and your share of that benefit is capital B, which is bigger than little b. That's why I drew it bigger. Yeah. Does that make sense? And this could be many, many times larger because this is half of a stag. Yeah, and this is a hare. Yeah, so smaller. The riskiness comes into the case that if you're the only one who decides to do that, your chance of success is small. And you could assume lots of things here about how the chance of success declines with how many people are helping you, but I'm going to make it super simple to analyze and just assign it to 0. You've got no chance of succeeding if the other individual doesn't help you, which is an extreme version of the model, but it brings out all of the texture that I want today. And then the final thing is, if you do the safe thing, it doesn't matter what the other individual does. Right? You always get little b. So the other individual's like, I'm going to go hunt a stag, and you're like, have fun. And you set some snares, and you catch a hare. Okay, let's analyze this model. This model has fun dynamics. It has different dynamics than the models we've seen so far. First, we ask, remember our guide, we're going to ask if there are any ESSs. So, safe is an ESS. When the payoff against itself exceeds the payoff of a a rare risky. Yeah, so it has to beat, risky gets 0, right? Yeah? The rare invading risky gets nothing. So it's always an ESS. Yep. We're going to assume that's always true. All right. And then risky is an ESS when big B is greater than little b. Do you see that? I should pause for a second. I may be going too fast now. Yeah? Again, think about it again. It's to do the ESS analysis. What does the common type get against itself? What does the invader get against the common type? Yeah, everybody faces the common type. And so 2 riskies are doing great. They're hunting stags. They're bringing back lots of stag meat. That's capital B. And there's some mutant who's like, I don't want any of that action. I'm going to set some snares, and they get less. Okay? So this is also always true. Yeah, by the definition of the game, right? But we didn't see that. So again, I want to bring this back to you. I think this is cool, no matter how many times I teach this stuff. You set up the payoff matrix, and yes, everything is there. All of the analyses that will happen are because of the assumptions here, but still you cannot see it until you do it. Yeah, you have to do the analysis to figure out the implications. So now we've got this situation. I'm going to redraw the game. And up here we've got, yeah, safe and risky. Yeah, it's like hawk and dove. And I've just showed you that this is an ESS, and so is that. Always. And now, the question would be, what's going on in here? Right? The arrows can't go both directions for the entire number line. Presumably, and I will show you how to analyze this, but presumably there is some range of values in here which will take you up to the all risky world where everybody hunts stags, and some range of values that will take you down to the safe hare hunting world. Yeah. If we could plonk you randomly on this line segment, right? There would be local dynamics at different points, and there should be some place on this above which you go up and below which you go down. It has to be true, actually. I'm not going to show you the general proof, but I'm going to show you how to find the point in the middle. And this is super important because then you get these, what are often called basins of attraction. I'll write that. Basins of attraction for the different equilibria. So this point here is not a candidate point for a long-term evolutionary outcome because it's unstable. Any little mutational event or migration or drift in the neighborhood of that is going to take you to one side or the other. And then if natural selection gets its way, which is what we do in evolutionary game theory, we ask what happens if natural selection gets its way. We know it won't in nature, but it'll get some of its way in nature, so it's worth analyzing what it wants. It'll either go up or go down from that point. So that's why it's important to find points like this, these unstable points. Yeah, Christine.
Can I say something about this model? Because I find this a super interesting case, what you show there, because this shows completely how rational game theory actions on the payoff matrix.
Yeah.
Because if we would, we have this really special case here that it isn't actually always fully frequency dependent, right? If you go for the safe option. So this means actually we don't consider any psychological effects, like you want to go for social,
right,
avoid social uncertainty.
Yeah.
So it doesn't actually mean that if we consider for this risk factor, not the risky strategy, but the risk factor that the other player does not make the rational move, that the basin of attraction could be stronger on the safe side? Yeah,
so yes, I think I know where you're coming from. And since, this is the evolutionary game theory I'm teaching you right now, there's no imaginary play is what I'd call it. So in general game theory, there's this important thing. So like if you're studying humans, as some of us do, and you want to predict their behavior, you do a lot better if you have some kind of minimally cognitive model where they're doing what's called imaginary play, which meaning they're imagining the consequences of their actions based upon beliefs about the payoffs. People do this. People, completely uneducated, illiterate people do this. So if you want to do game theory, behavioral game theory with real humans, it makes a lot of sense to do that. You can do better. There's none of that in this. We're assuming, I don't know, cells in a petri dish cooperating chemically or something. It's very simple. And that's what we can learn with. But yeah, those cognitive things, the fact that people do imaginary play in games of this structure, as you know, has big effects because people, they don't learn purely through reinforcement. Yeah, about how to play games like this. But that's a whole other topic. And if some of you develop strong obsessions for game theory, I can point you to all the stuff you want because I have that obsession. But yeah. Yeah, that's absolutely. So it's about theories of rationality blending into these basic evolutionary dynamics. But that's definitely level 2 of what we do. Okay, basins of attraction. We're on time. Good. So let's find this internal unstable point. We want to find this internal unstable point because it tells us which sets of initial conditions in a population will lead to the happy outcome. Individuals doing the risky thing together, and which initial conditions lead to the unhappy outcome. So we find that exactly the same way we found the internal equilibrium last time. All the symbols are different, but the basic formula is the same. And remember, the way to do it is to find the expected fitness of each strategy as a function of the frequencies of the strategies, and then set them equal to one another, because that's the question we're asking. What values, what frequencies of the strategies will make these things equal? I'm going to walk through these steps with you, but that's exactly how we translate the question into the algebra. So the first thing is to say we want the fitness of safe. I'm going to let P be defined as the frequency of the risky strategy. So the expected fitness of safe is P of the time it meets a risky, right? So now we're imagining a mixed population. There's some risky out there, there's some safe. Let P be the frequency, the proportion of the population that has the risky strategy. We have, just for today, although I'll end this in a moment, we have completely random assortment into groups. Your genotype has no effect on who you meet. And so P of the time you meet a risky. And what happens when safe meets risky? The same thing that always happens to safe. They get little b. So now you're saying, why all that talk, Richard? Because you got to derive it, right? You got to earn it. Yeah? All right. The rest of the time, 1 minus P of the time, you meet another safe, but the same thing happens. Yeah, exciting, wasn't it? This simplifies to little b. Yeah, so all that P nonsense. But the P nonsense is there because it's the definition. That's the expression that we needed. It just, in this case, it simplifies to little b because that's all that ever happens to safe. This was the point that you started with, Christine, right? The frequency dependence acts asymmetrically here.
Yeah, because it's such a common statement about game theory that's always frequency dependent, right? But actually, it's not necessarily like this.
Some strategies are not. Yeah, exactly. And yeah, and then risky, right? So risky meets another risky, and it gets the benefit of patrolling and no, wait, sorry, I'm in the wrong model. Which model am I in? Yeah, okay, so 2 riskies meet and they get capital B. This will be even easier. So, and 1 minus P of the time, you get nothing. Yeah, because you met someone who didn't help you. Then we set these equal to one another. I think I have enough space here to do this. So this is just B equals PB. Didn't this reduce nicely? Because I defined the symbols. So, folks, see how I got here? Yeah? So this is this, and this is all that remains of this because the 0 goes away, remember? Pick some variable, make it 0. Yeah. It's a great strategy. There's this great little book by Polya, who's one of the greatest mathematicians of last century. It's called How to Solve It. It's a great little book, and it's got this list of like how to solve mathematical problems. And I think number 3 is solve a different problem, right? But no, there's a whole chapter on it where he says, yeah, you can't solve that problem, stop. Solve something, you define a problem you can solve and then work your way back, right? And so there's a ton of that goes on in applied math like this, where biologists, they don't understand coordination, so they study this, which is not the problem they wanted to solve, right? But the idea is that we can solve this. That's its virtue. It's got all these problems, but we can solve it. Isn't that wonderful? And then gradually, we want the literature to reconnect with reality, but you have to move slowly and understand things one bit at a time.
Sorry, question.
Yeah.
Why is P or capital B there? Because P is the proportion of safe, or is the proportion of whatever is in the...
It's proportion of it's a proportion of risky.
By the above is the proportion of safe, no? In the WS.
This is the fitness of safe,
Yes.
and this is the fitness.
P is the proportion of whatever fitness you are.
No, it's what I defined here. It's the frequency of risky.
Frequency.
Yeah, you could look at the number line and get it. So here it doesn't matter. For safe, it just doesn't matter. They always get little b, no matter who they meet. Here, risky, you meet yourself, then you get big B. If you're unlucky, then you get 0. Okay, so we just have to solve this, and this is little b over b. Yeah, which is this point right here. So let me talk you through this a moment to give you some intuition about this point. This defines the unstable point between 2 basins of attraction, which are 2 regions of frequencies of the risky strategy that will either lead natural selection to favor it, so it increases, or disfavor it, so it decreases. And the way you want to think about this is, for both of these strategies, if they are sufficiently common, then they are favored. And we call this positive frequency dependence. Positive frequency dependence. Apologize for my handwriting being awful. This is in the notes. Yeah, that's my excuse. So they live well with themselves in this particular way, but there's still a social dilemma because one of these outcomes is better for everybody than the other, right? Again, this is why it's a cooperation dilemma, even though it's got different dynamics. I mean, no one's being exploited here, right? There's no clearly pro-social or anti-social option. But everybody would be better off if they could do the risky thing. The problem is, when risky is rare, it can't increase. Yeah? That same story helps risky be stable when common, right? Because it lives well with itself. And rare, safe hare hunters can't increase when rare either. But this is this kind of dilemma that arises from this. So if, for example, little b is very small relative to capital B, then this point is way down here. And then you can start to imagine, say if it's 1 over 100, you can start to imagine that you don't need very many risky hunters for it to start increasing in frequency. So the location of the domain of attraction is of interest quantitatively. Yeah. If you can get it small, then maybe you just need a little bit of coordination, which is what we're going to talk about next. Good? All right. Am I doing on time? I'm doing really well on time. This is great. Absolutely great. Are there questions? Moment? Okay, where have we been? We're at the pivot point in the lecture, so it's going to get exciting now, I promise. So I shouldn't make promises like that. But where have we been? Okay, so last time I showed you basic evolutionary stable strategy analysis under the disguise of a model of conflict, the hawk-dove game. I wanted to show you today is that same model labeled differently. Same model meaning the same equilibria and evolution dynamics can feel like a cooperation model. Yeah, you think about dove being a cooperative strategy that resolves things in a nice way. Hawk being the uncooperative defecting strategy. And in the hawk-dove's version of the model, hawk is taking action. Right? In this version of the model, the uncooperative strategy is doing nothing. So these models are different biologically, but we're not modeling that part of it, and that's what gives them the same evolutionary dynamics. I mention this because we're going to return to it in a couple weeks, and I'm going to have some examples with cooperation models where doing versus not doing, I think, matters a lot when you model real behavior. Just an assertion, right? So I don't have a proof for that, but I'm going to have an example where it intersects with mathematical modeling in an interesting way, because doing sometimes means you do things wrong, and once we start modeling errors, yeah, question?
Yeah, sorry, my brain's just stuck on
the
question that you have concerning the visualization of the line.
Yes.
So basically it's from 0 to 1, right?
Yeah.
So my question is why is safe on the left side? Why is safe 0?
It's arbitrary. You could draw the same thing and flip it. So it's a good question. Yeah, it's whichever you want to draw. So and for this model, it would affect where this is. So we could flip them. It just changes the definition of P, and then it'll put this on it's like it mirror images the thing. So this would be
so what is the definition of P right there?
It's the frequency of risky.
Frequency of risky. So then would be the frequency of safe.
Yes, and you could redo the whole thing that way. And I'm tempted to do it right now, but this seems like a great exercise for the student.
Yeah, I agree.
But it's completely arbitrary which you label with P. You just have to redo the derivation with that in mind, and you'll get the same results. They'll just be mirror imaged, right? So if this internal unstable equilibrium had been up here, it'll be down here now. It just flips the line. It just reflects the line.
And the same also then would go for
Yeah.
the equations.
Yeah.
You know, like if I flip so P and 1 minus P.
Yeah, you just come down and rewrite these so that you exchange every P with a 1 minus P, and then redo the derivation, and you'll get the same. It'll just be it'll be reflected from what it was before. Yeah, but exactly right. Yeah, your brain was focused on a relevant thing, so that's how it works. It's completely arbitrary. It's hard to get away from that this label invariance is what a nerd like me would call this. You get systems where there's label invariance, and these kinds of things, you have to deal with that. In statistics, we deal with it a lot too. Those of you taking my stats course or will have the joy of doing so in the future. There are lots of stats models that have this label invariance problem as well, and sometimes you have to pay attention to it. But that's why they pay me. So solve your label invariance problems. Anyway, other questions right now? Good? Yeah.
Regarding the P, which is the frequency of the risky strategy, what is the limit of those values? So if I have small b divided by capital B, if the benefit of the risky strategy increases, the frequency decreases, so what does that do? Is it bound between 0 and 1?
Yeah. It's a frequency. Yep.
Also the benefits?
Well, the benefits are units of fitness. So when you this is important. You think about B and little b, they have units. They're measured in offspring or nutrition or calories or something. But since there's a ratio of them, it's unitless. The ratio is unitless because the units divide out, which is what you absolutely need for a frequency because proportions are unitless. Yeah, and then I think your question is, but you can choose values of little b and big B such that they're not in the valid range, right? But then those are constraints on what those can be, yeah, for the solution to hold, yeah. But I don't think, I mean, these have to be greater than 0 because they're, yeah, so in that case, I think you're fine. As long as little b is less than big B, which is an assumption of the model, then I think you're fine. Yeah, it'll always be valid. But you can get cases where you can choose values that are invalid and that tells you where the solution set is. And maybe there's some interesting thing that hasn't been modeled. It's a good area to probe on the corners of your model like that, I think. Okay. Right. Now let's do, I want that. Okay. So. I want to talk about assortment now. All right, I will delete all that as we go. All right, so I'm going to take that model and put it over here because I want to refer to it. So I think this is the model I'm going to use to do everything. Okay, both of these scenarios are not particularly encouraging, right? So I had, well, I've erased one of them, sorry. But whether we were in the territory scenario or we're in the stag hunt scenario, it's hard to get cooperation to evolve, right? Sometimes you can't even keep it stable when it's common, but at least in this one, if it's common, it can evolve. It can be stable. In the territory one, it was sort of hopeless, right? It was never going to be an ESS, at least under some range of conditions. So what is it then that could let cooperation evolve in nature? It empirically does. There's lots of good empirical documentation of cooperation outside of humans. Yeah, a ton in humans too, but the mechanisms in human are different than in other species, but we see cooperation. Lots of places, often quite costly cooperation, self-sacrifice, extreme self-sacrifice. How could that possibly evolve under natural selection? And there's a huge range of solutions which have to do with something called assortment, as ways for cooperative strategies to socialize with other cooperative strategies. They assort, end up in the same groups, end up interacting. And the mechanisms for that are highly diverse. So what I want to show you today is how assortment works in a purely statistical sense, this world's simplest assortment model. I'm going to make the world's simplest assortment model, and I'm going to blend it with the game theoretic models you've already seen and show you what it does if there's some assortment. And then in the coming weeks, so next, well, not next week, on Wednesday this week, getting ahead of myself, on Wednesday this week, we will study in depth reciprocity as a form of assortment, where you repeatedly interact with the same individuals and you can remember things about them. Oh yes, you remember. Yeah. And what have you done for me lately, right, sort of thing. And then next week on Monday, a week from today, we'll look at inclusive fitness or kinship as a form of assortment. Right? If you interact with your close genealogical relatives, how does that work? And then after that, we'll go totally into orbit with elaborate population structure assortment. Now, we'll blend it all, and I'll have examples where there's spatial structure in the population which effectively creates assortment. And we'll look at how selection works. But those are mechanisms, instantiations, each of them interesting in and of itself in unique ways, that are all going to be examples of the general statistical assortment I want to show you today. But we want to have it be conceptual and simple mathematically today, and then fill in some fun modeling specific things with specific mechanisms in the coming weeks. That's the goal, okay? So what do we mean by assortment? We mean that strategies are more likely to meet themselves. Likely to meet self. And that means all kinds of strategies, not just cooperative strategies, right? So cooperative strategies want to meet other individuals like themselves, right? Natural selection would favor it if cooperative strategies could meet other cooperative strategies, or they'd be more likely to favor it. But uncooperative strategies will also meet themselves more often under some mechanism of assortment, right? And that's the thing that's really important in these models, is that assortment helps some strategies and it hurts others. Yeah. So what we're going to do is introduce the world's most basic assortment model. And the way we're going to talk about it is, now you remember I had some general fitness definition before, the fitness of some strategy X. I put the X there so that you don't mistake it for a strategy we have talked about today. This is strategy X. Beats all other strategies. Yeah. But there's a general definition for this, right? In a game with only two different strategies, say X and Y, we want to know the probability that you meet an X conditional on being an X times the payoff you get when you're an X who meets an X. And this is just the general notation, but remember with the models you can walk this through. So far, the probability you meet an X conditional on being an X is just the frequency of X in the population. Yeah, so when X is common, this is approximately 1. When X is rare, it's approximately 0. And that's what made the math so simple, is because if we're doing ESS analysis, one of the strategies is rare, and we replace its frequency with 0. Yeah, because we're looking at what happens right at the margin when you're the first of that type. Does this make sense? We're not going to do that right now.
Sorry, I wasn't paying attention. What is V again? V?
V, this is the payoff. Yeah. And then there's the probability you meet a Y conditional being an X. That's the payoff to an X against a Y. So like in hawk-dove, if the fitness of a hawk is the probability it meets another hawk, and we made that random before, there was no assortment, so this is just the frequency of other hawks, and this was the payoff you got when you were a hawk and you met a hawk, which remember is V minus C over 2. Yeah, it's burned into your brain forever now. Yeah, you'll teach everybody you meet about hawk-dove. The probability you meet a dove given you're a hawk, which was just the frequency of doves before. That will change in a moment. That is the payoff to a hawk when they meet a dove, which is V. Yeah. But this is true of all two-strategy, simple game theory models. And what we're going to do to model assortment is mess with these expressions. Mess with. Since we're all applied mathematicians, we know how to make expressions which do things. Oh yes, welcome to the expression shop. And in the expression shop, I have on offer a statistical assortment model, which gives us the probability that you meet your own type, conditional on being of that own type. There are two sorts of things that can happen. We're going to invent a new little symbol called little r. And little r is the chance you assort. I told you this was purely statistical. There's no biology here. I wave my wand and I say, R of the time you assort and you meet your own type. Yeah? I know it's sketchy, but next time on Wednesday, I will make this better. Yeah? And then there will be kinship and stuff, the lecture after that. The rest of the time you don't assort, but that doesn't mean you don't assort. I'll say it again. The rest of the time you don't assort, but that doesn't mean you don't assort. No, you don't assort through whatever assortment mechanism has the probability R. So 1 minus R at the time, but you could still meet just by chance, right? So if your strategy is super common, even when you don't assort, you could meet yourself. Yeah, and so we want to put put it this way. Let's call it little p of x is the frequency, the proportion of the population that's type X. Yeah, which could be little p. Yeah, question.
I'm sorry, I kind of blacked out. What does me self mean?
Another individual of the same strategy as yourself. Yeah, so it's, again, the probability you meet an X conditional on being an X is R, which is the chance you assort with your own type, through some mechanism that I am going to leave until the next lecture, and the one after that, and the one after that. Yeah. If you don't assort, you could still end up paired with an individual of the same strategy as yourself if your strategy is common, and this is the proportion of the population that's of type X. Does that make sense? Yeah, Christine.
Why you hit is actually small p now because it's actually the same as the probability, isn't it?
You mean this?
Yeah. So
I just needed to invent a...
Precisely to say now we're talking about proportion, but actually it's absolutely the same like the frequency, right?
Yeah, this would be exactly, it's the expected value of an indicator variable.
The frequency and the probability.
Yeah.
Okay.
This is the proportion of the population that is X. Yeah. It's the expected value of the indicator variable for if X is, yeah.
I get it.
Yeah.
When I was writing up now, I would also have used this PR. So this is actually my question, because it's the same, isn't it?
Yeah. This is probability theory notation. P is the most overloaded function in all of mathematics, right? It's just, think about stats notation. There's one function, it's little p, and everything will be called that. It's a nightmare.
This is exactly why I asked this question because it can become confusing, right?
Yeah, exactly. And so I had to invent some notation on the fly here, but you understand. All right, I didn't want to put just little p because then I had to say what little p meant and it just gets out of hand really fast. So this implies definitions for the other things too. The important one being, what's the probability you meet a y conditional on x, you meet an individual of another type. So that means the assortment failed, right? So we're only in 1 minus r land. But then you can meet y's anyway, just like you can meet x's anyway. Yeah?
Can I add to Christine was saying that conceptually, PR of x over x shouldn't be just dx?
Huh?
Because that's the probability of finding somebody who is your own.
I don't think that was Christine's question.
No? Okay, that's what.
But you have a question though.
Yeah. But conceptually,
Yeah.
the probability of, if you are x, finding somebody
Who's x?
should be independent of r.
No, that's the whole point. We're making a model where the probability you meet your own type depends upon this assortment mechanism. So r of the time you meet your own type, 1 minus r of the time you meet someone at random.
Yeah.
And so the chance you meet your own type under that event is the proportion of the population that is that type. So if we make R 0, we get back to the previous model, which is what I'm about to do. So if you turn off assortment in this model, which means make little r 0, then this term goes away, this goes away, and you're just back to px. And the same thing happens here. This becomes py.
So assortment is making you more likely to find somebody.
Exactly. This is positive assortment. You can make negative assortment models, but no one does. But there's no reason in principle, right, that negative assortment can't happen. Yeah. There are some social situations where it feels like that's what is going on. All right. Questions? I'm happy to take tons of questions. There's no point in going fast if people don't understand. Yeah? Okay. So let's apply this. There's my eraser. All right, let's apply this to the model we've got here. Yeah. I do it on time. I'm doing great on time, actually. So let's do this first with the patrol model, right? Which I erased. But it's in your heads, right? So remember the patrol. So we've got rest and patrol. rest and patrol, you both rest, you get 0. If you rest and the other one patrols, you get B. If you patrol and the other rests, you get B minus C. And if you both patrol, you get B minus C over 2. Yeah? Now let's ask what happens with this model when we add assortment. When there wasn't assortment, remember, it was very dismal. Yeah? So we're going to assume B is less than C so that the cost of patrolling on your own is prohibitive. So it means that patrolling cannot invade when rare. But now I'm going to add assortment so that little r of the time, rare patrollers meet other patrollers. And I haven't told you why yet, and in future weeks we will discuss mechanisms by which this could happen. Right now it's just hand-waving applied math, right? There's some mechanism, if it has these statistical properties, what effect could it have on natural selection? That's what we're doing right now. So we use these expressions, but we translate it into the language of these mathematics. So we're going to write that the fitness of patrol is equal to, right, the probability patrol meets patrol. Yeah? Times the payoff patrol gets with itself, which is that. With me? So I'm just filling in the template. I'm going to fill in the template still with these PRs, and then I'm going to replace the PRs with these expressions. But I'm going to do it one step at a time. That's the probability you meet a rest, conditional on being a patrol, times what you get in that circumstance, which is B minus C. So let's put the expressions in, right? So this is going to be R plus 1 minus R times the frequency of patrol. So let me just assign P to be the frequency of patrol, okay? Oh wait, that's 1 minus P. Yeah. There we go.
When West meets, the probability that West meets patrol is at B or B minus C. Because if I rest and there's a patrol,
you meet a rest, you're a patrol, the probability you're paired with a rest given you're a patrol. And then you patrol, and you get B minus C.
I'm sorry, sorry.
Yeah. No, it's I understand. I'm very sympathetic. I'm super close to the blackboard. My IQ is in half right now. So many symbols, moving all over the place all the time. Okay, does this make some sense? I've just filled it in. All right. Now here's the magic moment. So far we've made no progress. We've just made the expression longer. It's like, gee, thanks, Richard, right? But now we're going to do ESS analysis again. And that means we're going to take P and we're going to ask what happens when it's big or small, close to 1 or close to 0. If it's close to 0, that's the thing we're interested in right now because we're going to do invasion analysis. I'm going to ask, is there any circumstance when patrol is rare that it could invade? I'll say that again. Is there any circumstance when patrol is rare that it could invade? In the absence of assortment, we already found the answer was no, because we're assuming B is less than C, so that the cost of one individual patrolling is prohibitive because their private share of the benefit is too small. Yeah? But we're going to stay in that world, and we're going to see what happens. And that means we're going to set P to approximately 0. We're going to simplify this expression, right? And so when that's true, this becomes approximately, there's a P, so that whole thing becomes 0. So we just get R, B minus C over 2. Yeah, that's assortment. And then that's a 0. So this becomes 1 minus r b minus c. I'm good at time. Is that a hand?
Yes.
Yeah, go ahead.
How can I say this? So before you wrote the r plus 1 minus r times p, I already wrote it like p, imagining it was 0. The question is, why is p? Why do
That's a great question. Why is P? I understand exactly what you're saying. So I wanted to show you the steps so this is the assortment model. And in the assortment model assortment is operating no matter what P is. And so the assortment model has the frequencies of the strategies in it. And I wanted to show you the whole assortment model because it'll apply the whole line. I'm going to draw the line up again for the model. Across the whole, all the possible states of the population, assortment is operating. It doesn't only operate when something is a common type. So I wanted to give you the whole assortment model like that has that in it, and then show you that at the limit, we can approximate this complicated thing because the P drops out. But we're going to need the assortment actually in the middle in a moment because it's always operating. And it's going to change that point where the bases of attraction are defined. So we're going to need it in the total expression. But I wanted to layer it in one step at a time because it kind of explodes. Good? All right. We got 15 minutes. We can do this. Okay. So yay, is this progress? What do we do with this? Do you remember? Well, we've got to compare it to something, right? We need to compare it to the fitness of rest under the assortment model. And again, this is the first example, so I'm going to belabor it, right? So we've got the probability that you meet a rest conditional on being a rest times the payoff you get. And when a rest meets itself, it gets 0. Plus the probability they meet a patrol given their arrest, and in that case they get B. So with the assortment model, I'm going to write it here, but you see it's going to be multiplied by 0, but I'm going to write it all out because that's how much I care. Yeah. No more. That's exactly it. But times 1 minus P times 0, right? They are the time they assort, so they'd meet another individual with the same strategy. 1 minus r the time they don't assort through that mechanism, but they might just get unlucky, right, and meet their own type. And since P is defined as the frequency of the other type, 1 minus P is the frequency of their type. Yeah? Plus, you don't assort, and there's a chance P that you meet an individual who patrols. Yeah, so this simplifies. It's just 1 minus r PB. But it's important to see the definition, right? And the magic 0 makes something go away, but that's just a trick. Yeah. And then we ask, and then we're letting P go to 0. And so if P is approximately 0, this is approximately 0. Right? Assortment does not help rest at all. Yeah. And then we can ask, is there a condition when this is greater than that? That would be a condition for a rare patrol to invade. I'll say that again. Is there a condition for a rare patrol to invade? The condition for that would be this expression exceeding this one. So we need r b minus c over 2 plus 1 minus r b minus c greater than 0. Is the logic clear? The rest is algebra, which, you know, either you enjoy it or you don't. There's nothing more to say. But let's do it, yeah? So the thing about applied math, when you end up at this wonderful point where you've written down the expression you need to do something with, and now you must understand it. And nobody can tell you how to do that. Nope, it's just how it is. However, I've already worked this problem. And so I can tell you that what we want to do is we want to rearrange this to isolate R. We want an expression, a condition in terms of R. Why? Because R is the strength of assortment. And so the implied question here is, how does assortment change the answer? We know the answer without assortment. The answer is give up. Yeah, it can't evolve. But with assortment, how does it change things? So we're just going to isolate R. I just pull the R's together. We've got a minus B plus C in there, and that has to be greater than, yeah, on the other side. You should be checking me. Sorry, I did something bad there. I did multiple steps. But someone should be checking me, okay? Because I can make mistakes. Ooh, these B's cancel. Oh, look at that. And this is going to be C over 2. And that has to be greater than minus B plus C. So this implies R greater than, all right, what do we get? We get minus 2B over C plus 2. Yes. So R has to be greater than 2, 1 minus B over C. Okay. And so there's all this stuff going on the right-hand side, and this is, I will walk you through it, because this is the thing that like no book will tell you how to do this. We've got a condition in terms of R, and it says if assortment exceeds something, then rare patrol can invade. I'll say that again. If the strength of assortment exceeds this thing, then rare patrol can invade. So hey, we win. Right? We assume some assortment happens, and it shows that if something is big enough, then rare patrol can invade because they'll find one another often enough. So you could imagine this is a number like a half, which would be a very large amount of assortment, but we'll think about that more next time we meet. And then you've got this expression, which is 2 times 1 minus the ratio of benefits to costs. And this looks like what? Just a result of the particular assumptions we made in this model about how costs are shared and how the scaling works. And if you change those assumptions, you'd get a different expression. But in every one of these cooperation style models, you get some function of the benefits and cost. The benefits and costs are very different relationships to one another, but the amount of assortment has to be large enough to compensate for the private gain of not cooperating. That's what all of these expressions tend to say. But the exact expression is just a feature of the exact economic model you assume about how behavior works. But the point is that, yeah, if you make assortment greater, it's easier to satisfy this for any particular B and C, and there's hope. The other, I have 10 minutes. Yes, I can do this. Can I erase this? Yeah, got this? So let me show you the other model too, because I think another example will help. The other model is this one. Let's go back to the stag hunt. So the stag hunt has this, both strategies were evolutionarily stable. And the problem is that there's this internal unstable equilibrium. So if we analyze that model, this will be a chance for me to show you why we need the full model, right? That was the question we had before. Yeah, let me write it over here. Okay, so risky, safe. We're gonna let P be the frequency of the risky strategy, and we already derived that in the neighborhoods of each strategy being common, selection favors that type. So assortment's not going to do anything on the ends, because assortment will only strengthen whatever positive frequency dependence we've got already on the ends. Both strategies are already evolutionarily stable. Assortment won't have any effect on that. It just makes them even more stable, right? Because now, if there was any marginal effect of meeting the nasty invader, they're avoiding that. Yeah, and nasty invaders meet one another, which is bad for nasty invaders. So assortment doesn't have an effect on the endpoints of this model, but it will have an effect on the location of the basins of attraction. And our mission as peace-loving, whatevers, peace-loving biologists, is that an expression? Peace-loving biologists is for the basin of attraction to get small enough that even very small groups of migrants could get a foothold and transition to the nice welfare-enhancing state. That's the big thing in this model, is that there are two equilibria. There's an equilibrium down here and up here. But this one is actually bad for the population. Everybody would be better off if they could just teleport up here. But you can't teleport in evolution. You have to evolve. And it is a struggle to do that. And that's what's going on in this model. Right. So we're going to write the fitness definitions for that model using this definition. So the fitness of the risky strategy under an assortment model is the probability it meets itself, which is R, 1 minus R P, times what it gets when it meets itself, which is capital B, plus 1 minus R, 1 minus P times 0. Okay? Was that all right? I just used this and the assortment model. Yeah, this. The fitness of safe. Chance it meets itself. Times little b. Plus the chance it meets the other type times little b, which is, shock, little b. But it's important to do all I mean it. It's important to write it all out, and so you don't prematurely badly simplify something. Yeah. So to find the location of the internal unstable equilibrium, which defines the basins of attraction for the two outcomes, and remember we care because the safe outcome is not welfare enhancing. There's all of this biological soma to be had in the world, and the population would capture it better if they could just do the risky thing. Yeah, was that a question, Christine? No? Okay, sorry. This thing with being a teacher, you interpret everybody's personal grooming habits as asking a question. It's very, very dangerous. It's my problem, not yours. Okay, so we find that the same way we find all equilibria, we set these things equal to one another, and we ask, is there a value of P that will make that true? And so we say, yeah, so we get R plus 1 minus R P B equal to little b. It's not bad, as an expression goes. Yeah, question?
If we say that the same strategy is not socially beneficial, then shouldn't we be making the fitness of R greater than the fitness of S?
Well, we're finding an equilibrium right now, so we want to know when their fitnesses are the same, because at the internal, it'll be in here somewhere, and I don't know where yet, but it'll say it's there. At that exact point, the fitnesses are the same, but if you go above it or below it a little bit, then they're unequal and it runs away. So that's why we set them equal. Yeah, because it's not an invasion, it's an equilibrium point. That is a weird thing, though, about this kind of equilibrium, is it's still an equilibrium. It's just not a candidate for a long-term outcome because the population won't stay there if you perturb it. Yeah, but I remind you from last time, the two basic flavors of equilibria in these sorts of models, the stable ones and the unstable ones. And the stable ones are candidates for what could happen in the long run because the system will go there from a range of initial conditions. So these are stable equilibria on the end. And we're finding the unstable equilibrium that creates the range of conditions that leads to those. Yeah, but the other thing is also an equilibrium, and you find it exactly the same way you find all the others. But then the stability analysis is something else you do. Okay. Right, so let's solve for this. So we get R, 1 minus R, P equals little b over big B. And yeah, is this going to solve nicely? It is not going to solve very nicely. No, it'll be fine. Yeah, this is fine. 1 minus R P equals little b over B minus R. What does that simplify to? That is not going to simplify to anything very nice, is it? Yeah, but that's okay. It's all right. It's fine. It's that. Let me give you the intuition for it. All right. So the previous point was little b over b. Remember, we solved it before. It's in your notes. We found the equilibrium, the unstable equilibrium before was at b over little b. This expression is less than that if r is greater than 0. Yeah, and it's not super easy to see it, but even in my notes, I don't have a way to write it that removes this problem. Sorry, but it's fine. And it moves it, say down here. I'll make a square, right? And then we get this new expression that's lower than that. So why is that? Assortment is increasing the domain of attraction for the welfare enhancing strategy. Why? Because the welfare enhancing strategy benefits more when it finds itself. And so assortment benefits it. Not just at the end where it makes it even more super stable, right, than it was before, but under a wider range of initial conditions, natural selection will lead to that outcome because assortment favors it more. Does that make sense? So these general statistical assortment mechanisms, they're like welfare finders, right? They benefit the strategies that generate more goods for the group. Does that make some sense? Yeah, question?
Could you say that again, please?
Which part? Yeah, so assortment favors, in this model, assortment favors the strategy, meaning the basin of attraction. So the internal equilibrium that defines the basins of attraction moves to the left, which means that the basin of attraction for the welfare enhancing strategy, for the risky, in this case, stag hunt, is increased. So assortment has favored, that is, if you think of it this way, what are the range of initial conditions that will lead to the risky strategy being evolutionarily stable or lead to it evolving? And the stronger assortment is, the larger the range of initial conditions are that lead to risky evolving. That's because assortment helps it more than assortment helps the other strategy. Assortment doesn't help the other strategy at all, actually. And this is Christine's point again. Assortment is an asocial strategy in a social game. We've all know that guy, right? Comes to the talks, takes pizza and leaves, right? That guy, sorry. And so, but natural selection will be your judge. And if there is assortment, then assortment favors the strategies that produce common goods. Yeah. So that's what I wanted to give you, is this sense about how this thing ends up migrating as you increase R. And if you make R 0, you get the original one back. This is the kind of check you want to do on your solutions always, is if you have made a specialized model from a previous model, your previous model is a way to check yourself and make sure you didn't make a mistake. You should be able to set certain variables to 0 and get the old model back. So this is this constant feeding stuff in, yeah? Yeah, question?
Shouldn't you go closer to the risky strategy when you have assessments?
It goes assortment. It goes the other way because a large basin of attraction it means more initial conditions lead to this.
Okay.
So it gets bigger rather than getting smaller. And smaller is bad because then there's a very tiny range.
So you increase the
Exactly. So the unstable equilibrium, if you were a strategy, you'd want the unstable equilibrium far away from your pure point. Yeah, because then there's a bunch of conditions that lead to.
R goes to 1, basically you're
Yes, then you've got the whole line. Yeah, if R goes to 1, you get the whole line. Absolutely. So you can substitute that in. We take the limit as R goes to 1, right? So this will get really big. Yeah. That'll get big pretty fast when you're dividing by 1 minus R. Does that make some sense? Our time is up, and I like to stay on time. But I covered all the important stuff I wanted to. I want to remind you that my handwritten notes are on the website too. That's what I'm teaching from, and some people have told me they like these. So whatever embarrassments and misspellings there are in them, I hope you find them of value. On Wednesday, and there's a homework problem up on the website for this too that I think is easy. You know, not to set you up for personal disappointment, but I think it's easy, and I believe in all of you. On Wednesday, we're going to pick up straight from here, and I'm going to do repeat behavior, how to model meeting the same individuals over and over again. Okay? Thank you for your time.